and the factors are going to affect diffusion. Again, the course of oxygen transfer, specifically Fick's law of diffusion, defining DL, and understanding, again, what effect that a reduced alveolar oxygen will have on diffusion. So we'll kind of go through these properties in this session. So we're going to start out here first with the figure. And so overall, what the figure indicates is this is the total amount of oxygen that exists in the blood. And what it is dependent upon is a function of arterial PO2. As we indicated, normal arterial PO2 at sea level breathing room air is 100 millimeters of mercury. And if we come up on this graph and we look at this point here, to look at the oxygen content, so this is oxygen content, it's mLs of oxygen per deciliter of blood. Keep in mind, a deciliter is another way of saying 100 milliliters. So sometimes in these figures, you'll see either deciliter or you may see 100 milliliters, but it's the same convention. And so what we're going to look at then is the total oxygen content is about 20 mLs of oxygen per deciliter of blood. But how it's broken up to is the total is shown up here in brown, but it's the sum of the red and the yellow. So the yellow is dissolved, and the red is oxygen bound to hemoglobin. So if you take the red, you add it to the yellow, what you end up getting then is the total, which again is about 20 mLs of oxygen per deciliter of blood. And what we're going to, for this session at least, and the next one is pay particular emphasis to is dissolved oxygen, understanding why oxygen is dissolved and its properties in that form and how it mediates diffusion. So we're going to be interested in the dissolved form. And so just a couple observations or facts. Only what we know is only dissolved gas can diffuse across the blood-gas barrier. So what we're talking about is, again, the movement of oxygen from the alveoli into the blood. It has to be in a dissolved gas form, which is going to have a certain partial pressure to it in millimeters of mercury. Indicated here, only the dissolved gas contributes to the partial pressure of gas in the blood. And any oxygen that's bound to hemoglobin does not exert any partial pressure as far as millimeters of mercury. And the driving force for diffusion of this gas is the difference of the partial pressure. So in other words, how much oxygen and how quickly and how efficiently it moves from the alveoli into the blood is dependent upon that delta P. And what we know is, again, the alveoli normally set up at 100 millimeters of mercury, and the oxygen coming in on the venous gas is about 40 millimeters of mercury. So that is the delta P, which will drive the diffusion of oxygen from the alveoli into the arterial blood. And so specifically what we're going to talk about then for dissolved gas is Henry's law. And what Henry's law says, the concentration of a dissolved gas is equal to the solubility of that gas times its delta P. So how much, again, and this comes down to the concentration of oxygen in the arterial blood, again, in its gas form that will be exerting this 100 millimeters of mercury, is its solubility times that delta P. And these two factors will determine ultimately what that concentration is going to be. So the path of diffusion, again, just to understand this, so over here is an alveolus. Again, we've overcome, let's say, a compliance and lung resistance, airway resistance, and we've got 100 millimeters of mercury set up here. And this is a red cell that's coming in. And in the venous return blood, as we said, the partial pressure of oxygen is only 40 millimeters of mercury. So there's a driving force to drive oxygen from the alveolus over into the capillary. And the important thing is oxygen will stop diffusing when it reaches equilibrium. When the pressure here in the arterial blood reaches essentially 100 millimeters of mercury, equilibrium will have been reached, and at that point you'll no longer see diffusion across this membrane. The important thing to keep in mind, again, is the mechanism of oxygen moving across this membrane is passive diffusion. Again, it's not an active transport. There's no oxygen carbon dioxide co-transporters. It's simply passive diffusion mediating this process. And we talked about previously that it ends up being under normal conditions, a relatively small path of diffusion. And you have to get through the alveolar fluid, which is mainly the surfactant, the lining, the alveolar epithelial cell, the basement membrane through here, the interstitial space, the capillary basement membrane, the capillary endothelial cell, actually diffusion through the blood itself, and then finally crossing through the red cell membrane. And once it makes it inside of the red cell, it will bind hemoglobin very efficiently. And what's important is when it binds hemoglobin, at that point, that oxygen is taken out of solution, is taken out of its gas form, and at that point, it's no longer exerting a partial pressure. It's bound to hemoglobin, and again, is not existing in its soluble form, and therefore is no longer exerting a partial pressure. On average, a red cell will spend about 3/4 of a second in this pulmonary capillary network. During that time, it traverses about 2 to 3, usually about 3 alveoli. And again, certainly that is more than enough time. This 3/4 of a second is more than enough time for diffusion to be complete, where the oxygen can come across, reach equilibrium over here on the blood side, and again at 100 millimeters of mercury. And at that point, there's no more net diffusion. And so, as I indicated a second ago, what is important is to understand that the mechanism by which oxygen moves across this membrane is passive diffusion. It's not an active transport system. And therefore, it's moving across the membrane via passive diffusion. Essentially, what this means is it's following Fick's law of diffusion, the principles of Fick's law. And what Fick's law tells us, in order for passive diffusion to be effective, a few things need to be true. First of all, the rate of diffusion, so how much diffusion there is proportional to the area of the membrane, but inversely proportional to the thickness. So the important thing here then, again, is diffusion is better when the surface area is great. And as we talked about, there happens to be a huge surface area in the lungs, and the benefit for us is most of that is in the alveolar airways, which is where gas exchange takes place. So effectively, we do in fact have a very large surface area, and that's going to allow for good diffusion, but inversely proportional to the thickness of the membrane. Ideally then what we want is a relatively thin membrane, which is what we have under normal circumstances. But keep in mind, if disease thickens that membrane somewhat or significantly, the path of diffusion is going to be lengthened, and overall its effectiveness or the rate of diffusion will be decreased. So again, what we desire is to have a large surface area and a relatively thin membrane. And if you have those properties, then your rate of diffusion will be good. Diffusion rate is also proportional to the partial pressure difference. as we talked about. So a larger delta P is going to have more of a driving force versus a smaller delta P. And the diffusion rate is proportional to the solubility of the gas in the tissue, but it's inversely proportional to the square root of the molecular weight. Essentially, all this is saying is you want a gas that's reasonably soluble. If it is, it'll diffuse better. And essentially, what this is saying is smaller is better as far as size goes. It's inversely proportional to the square root of the molecular weight. The bigger you are, the less effective you will be. And again, if you're a smaller molecule, you will actually end up diffusing better. Smaller will give you better diffusion. And that comes with a caveat, and we'll talk about that in a second. So what this means then is kind of understanding Fick's law of diffusion. So the diffusion of a gas through a membrane, and this is Fick's law, this is diffusion, V dot is proportional to area over thickness times D, which is the diffusion constant derived from solubility over molecular weight times delta P. And again, delta P is the pressure gradient. So what this means here then is what becomes important is to be able to understand what these different factors, say for an exam, in this case, is if I tell you that an area has been reduced by 50%, a thickness has been increased, by 300%, being able to predict what will happen to diffusion, again, understanding who's proportional and who's inversely proportional with respect to diffusion and the flow of gas, the flow of oxygen across this membrane. But these are the variables, and the reality is that this D is essentially a constant. Again, it's solubility and molecular weight, and that's really nothing that we can change. Essentially, what disease changes is disease will either decrease A or it'll increase T, and that's what we'll tend to see in pulmonary disorder. And really what that leaves for a practical purpose is if area goes down or T goes up, which happens in disease, but the only thing left here in this equation for us to deal with, or at least to play with in order to maintain diffusion, is to increase the delta P. And this really is where the idea of supplemental oxygen therapy comes in. So having gone through the alveolar gas equation, we understand if you put someone on 100% oxygen, what effect you can have by again 100% oxygen at sea level. You can get alveolar oxygen up to 663 millimeters of mercury. So that's and if it's coming in at 40 in the venous blood, again, now you have a much larger delta P than 100 versus 40. Now if you go with the supplemental oxygen, you can go up to 663 versus 40, again, which is a larger delta P. So what it comes down to, one way to look at this again, is if disease is decreasing your A or increasing your T, which will impair your diffusion, what you're really left with then is to ramp up your delta P to compensate that. So a simple way is if you lose, let's say one lung has to be removed, so you lose half of your surface area. If you want to maintain the flow that you had, you'd have to double your delta P to account for that. So that's kind of a good way to think about this equation. And again, principally what you'll see is disease is decreasing A or increasing T. And so then what becomes of interest, though, is kind of the clinical aspect of this. And so again, Fick's law of diffusion for the lung. And so we talk about the surface area, and we talk about the thickness. And the question becomes, how do you physically measure this? How do you measure this, the surface area, the diffusion capacity of the lung? How do you specifically measure in square centimeters or square meters how much area is in the alveolar airways? And the reality is physically you can't do that as far as with a ruler or some type of measurement, but what it can be measured is essentially functionally. And so what Fick's law of diffusion for clinical purposes gets represented now is to flow equals DL times delta P. And DL is the diffusion capacity of the lung for a particular gas. And what it includes the area of the membrane, it includes the thickness of the membrane, it includes the solubility, and it includes the square root of the molecular weight. So basically A, T, and D all get lumped into DL. And as I indicated a second ago, keep in mind that both solubility and really the size don't change. And so what you're really considering then is this changes either in area, such as a decrease in surface area, or an increase in the thickness of the membrane. So what this means then is the diffusion capacity for a specific gas, let's say in this case oxygen, is going to be equal to DL times delta P. And if someone comes in the clinic and they either have a decreased area or an increased thickness, is what you would end up seeing then is overall a lower flow for this particular patient. And again, how you ultimately would change that is through delta P. So we're going to focus on this equation here a little bit more. But again, what we want to take away from this slide is we physically cannot measure the surface area, the thickness, with either calipers or rulers or anything like that. So we're going to functionally take all of these constants, A, T, and D, and lump them into this DL, which we're going to measure through a different gas. And so this raises the question, how is DL measured clinically? And so DL is the diffusion capacity of the lung. And again, it's largely set up by how much surface area we have and the thickness of that membrane. And it turns out carbon monoxide, so this is the same carbon monoxide that's lethal. It comes out of car exhaust, and it comes out of heaters and things like that. So carbon monoxide is used to measure DL because it is diffusion limited. So the capacity of carbon monoxide is a lot. It's entirely diffusion limited, and that makes it good for understanding the diffusion property of the lung. So what we then say is we say that the flow, the diffusion capacity, the flow of gas, in this case of carbon monoxide, the flow of carbon monoxide is equal to the DLCO. So this is the diffusion capacity of the lung for carbon monoxide times delta P. And again, and we're going to use this now to understand ultimately how appropriate is our diffusion capacity for the lung. And what we're going to then do to move from this equation is what we just want to set up now is to calculate DL. So we're interested in, again, because ultimately what we want to define is the diffusion capacity of the lung. So to get from, to solve for DL, what we just do is divide both sides by delta P, and that's what this equation shows here. So what this says is the DL, the diffusion capacity of the lung, is equal to the flow over the delta P. And so again, if we know the delta P and we know the flow, we can essentially solve for the DL. So how this is done then clinically, you have a patient breathe a small percentage of carbon monoxide. In this case, it can be 0.1%. The important thing again, this is the bad, the lethal gas that can be lethal, but not at this low concentration. So you have a patient breathing a small percentage of carbon monoxide. And then therefore what we know is the alveolar air, once it's equilibrated, is going to have 0.1% carbon monoxide, but the capillary blood is going to be 0%. And the reason why is because we don't produce carbon monoxide in our blood. So this is our delta P. So now what we know is we know a delta P, which is basically shown here in the equation. And then what happens is the carbon monoxide then is measured in the blood over time, and so the amount of carbon monoxide that's taken up in the blood is now the flow, how much actually made it across that membrane. So what you get is understanding a certain amount of flow, a measure of flow, you know the delta P, and that tells you the diffusion capacity of the lung. And so DL is measured, its volume is the amount of carbon monoxide transferred in mLs per minute per millimeter of mercury of alveolar partial pressure. And the way to think about this then is, so again, what we're doing is we're applying a certain delta P, and then we wait and we measure to see how much made it across. And there is a certain predictive value that there should be a certain amount of carbon monoxide that flows across. And in that case, that's going to give rise to a predictable DL. So a 21-year-old male should have a certain predicted DL measurement, again, in mLs of carbon monoxide per minute per millimeter of mercury. A 50-year-old man should have a certain DL, and again, certainly DL will change, obviously, with disease, but also with age. And so the important thing here to understand is that what we're getting at then is there's very specific predictive measures that we should be able to see. And as it turns out, let's say hypothetically that if someone, again, one lung is taken out for a medical reason, that means you would lose half your surface area. And at that point in time, the ability of carbon monoxide to flow across, again, at this delta P, if this delta P is 0.1, holding your delta P constant, but if you lost half your surface area, what you know is presumably your flow would go down by about 50%. And so losing, again, half your surface area would mean your flow would go down. And overall, what that would say is the diffusion capacity of the lung, the DL, again, would similarly be down by about 50%. So overall, the DL is saying that there's the capacity for the lung to accept a diffusing gas has been decreased. Now, again, it doesn't tell you necessarily what the reason is, but again, we know from fixed law of diffusion, it's either going to be a decrease in area or an increase in thickness. And again, so the important thing about this is if you have a fixed delta P that we know, just simply measure on the arterial blood side to see what the flow is, and that should be a predictable measure. If that holds up true, then the DL should fall within normal lines. But if the flow ends up being significantly less, again, less in the numerator by the same delta P means overall the DL is going to be less. And what that's saying is if DL is less, either surface area went down or thickness of the membrane is increasing in this case. So again, the DL becomes very important in understanding, again, the diffusion capacity of the lung factors in, again, the different factors that we talked about, and is indicated down here. The easiest way to think about it is if you, in theory, if you remove one lung, if you take away one lung out of this person, the ability of carbon monoxide to move across and diffuse into the blood will be reduced by about 50%. Again, we just lost half the surface area. And by that ability, this V dot being reduced by 50%, what that means is DL will be reduced by 50%. So again, DL is the capacity of a gas, the diffusion capacity of the lungs. And again, it should be a specific normal clinical value within a certain range, again, for a particular gender and age. And what you're looking for is a normal value. And if for whatever reason that value is less, again, it's telling you that what that essentially means is the flow was less at a fixed delta P. The flow is significantly less. And in that case, if the flow is less, it has to be due either to an increase in thickness or a decrease in surface area. So as it turns out then, and this is one of the things we talked about previously, is we know, again, surface area becomes very important. So where is the vast majority of the surface area of the lung located? Again, as it shown in this figure here, is the total cross-sectional area of the lung, plotted as a function of the airway generation number. Again, 0 is the trachea. Terminal bronchioles is 16. This is the last of the conducting airways. So again, it's the area under the curve, and what we really see is a very small area. And then again, most of the area in the lungs is from basically to the right, from 16 towards 23. Against the area under the curve, which is all of this, which is increasing exponentially. So the vast majority of the surface area of the lung, in fact, lies in the alveolar air spaces, and this is where the membrane surface area is large. And again, so what we want is to have that large area in the alveolar airways, which is where it is. And as far as the actual number, it's estimated to be about 75 meters squared is the surface area. The total surface area of the lung is about 75 meters squared. That's about the size of a tennis court, if you could lay that out and get a sense of how big it is. So that's the diffusion capacity, 75 meters squared. And again, based on this graph, we can see that greater than 99% of that is going to be, because this is exponential here, way up at the top. It's we're kind of going off the scale. So greater than 99% of our surface area will exist out here in the respiratory zone in the alveolar airways. And again, that's important because what fixed law says is we need to have a big surface area for diffusion to be effective, and that's where our diffusion is. We have both a large surface area, and we also talked about where the membrane is thin. As we got down to the alveolar airways, we went through this process where we shed the connective tissue. We just got down to the point where we pretty much just have the type 1 and the type 2 alveolar epithelial cells. So at this point, we do have a large surface area. It's relatively thin, and that will allow for very good diffusion capacity or very good DL within the lung. So summary of key points, again, understanding the concentration for dissolved gas, the path of diffusion being relatively short, the movement of gas across this membrane is governed by fixed law, and being able to understand if those different variables are changing, how that's going to affect diffusion, understanding what DL is, and again, how it's really a functional measure of really the anatomical properties. It's a functional measure of the surface area as well as the thickness of the membrane. And when DL goes down, it's indicating overall the capacity's gone down for some reason for a given delta P. And if the diffusion capacity has gone down, that will translate overall to a lower diffusion rate, lower flow of diffusion. Again, understanding that ideally what we want then is in these where gas exchanges is occurring, where oxygen is moving from the alveoli into the blood, it is in the alveolar airways and the respiratory zone. And again, that's where about 99 greater than 99% of our surface area lies, and also has to be relatively thin as well.